last Thursday, we derive a transfer function from the angle to electric torque that goes through the excitation system of the generator. So which is shown here. We have proved this one based on the a block diagram. And this one can be very useful to determine the component in parallel with the angle deviation and or in parallel with the speed deviation. So the first component will be the synchronizing torque. The second component will be a damping torque. For steady state condition, there's no oscillation, or oscillation can be ignored. So we only have synchronizing torque or synchronizing coefficient. But for the oscillating condition, if we consider some oscillation frequency, there will be a synchronizing torque or synchronizing component and also damping component. So when the synchronizing component is positive, which means that this generator tend to become coherent with the rest of the system. If the damping coefficient is positive, which means the oscillation will decrease the amplitude, will have positive damping effect. So ideally, we need to have both Ks and Kd be positive. On this example, we use some typical data. So when we increase the gain of the excitation system, the synchronizing coefficient will become from negative to positive and has increased value, which means the excitation system will have positive effect on the synchronizing the generator with rest of system, which means the system tend to become more stable in terms of maybe broad angle stability or transient stability. But the damping coefficient will become negative. So in order to avoid the negative damping, you may not increase the gain beyond a certain value. Otherwise, you have growing oscillation. But this gain may not be large enough to give you good voltage regulation. So there will be a contradiction. So either you pick a large gain to make a voltage regulated well. Also, you have a large synchronizing torque, but the damping torque will be bad. Or you have a positive damping torque, but the voltage regulation will not be good enough. So that issue can be addressed by power system stabilizer. But this issue may not be general for every generator. So only for the generator or locations you face such a dilemma, you want to introduce the power system stabilizer. Okay, but if the gain you put there doesn't cause the growing oscillation and can give you good voltage regulation, you don't have to utilize power system stabilizer. Power system stabilizer is only not required, but it's only optional. Okay. So what power system stabilizer or PSS does is just measure the frequency deviation and go through some transfer function. This is what you design for the PSS. And it will introduce another signal also to the exciter. So this signal has meaning of the voltage. It's like voltage signal because it's going to add it to the reference or add it to the feedback signal. But the input is a frequency deviation. We know the synchronizing torque or damping torque translate either the angle deviation or speed deviation to electric torque, right? But this PSS only translates the signal from a frequency deviation to a voltage signal. So this voltage signal still need to go through the exciter, the field circuit block, and all through until here to become finally electric torque. And this PSS is usually integrated in the excitation system. There's a just optional function there. If you want to use this PSS, you need to enable this block. Otherwise, this block is just open. It's not functioning. So it adds damping to generator by providing voltage signal, but they actually measure some non-voltage signal. That's why we call it auxiliary signal. So here is just speed deviation. We know that for typical excitation system, it measures voltage signal, then provide some control signal, also voltage, right? Remembering the control block for excitation system or AVR, all the signal are actually voltage. But here for PSS, it measures the speed deviation. So if this transfer function of PSS is just simply a K, let's say we just call it a K. Okay. And the K multiplying the speed deviation, if this one is completely, if the output is something like electric power, has meaning of electric power, this K, if you take a positive value, that K will be added to the KD, the damping coefficient, right? Because TD is as a component, damping component of the electric torque, which is equal to KD multiplied by delta omega R. This is definition. So this is like damping torque. If this is positive, this oscillation will decay, which means this, if KD is positive, the damping torque will be in the same direction of speed deviation. So if we make the output of this PSS be electric torque, and we make a K be positive, then this PSS will add damping, depending on how large K you put. If you put a very large K there, it will give you a lot of damping. But that's based on assumption if the output has meaning of electric power, or at least that one need to be somehow proportional to the electric power. But actually, because this one doesn't add any electric power to the machine part, they only just change the control signal, just add it to the reference voltage signal. So which means the output may not be exactly proportional to the electric power. Okay, so if this transfer function is a pure gain, and the channel going from this input all the way to the electric power is also pure gain. Pure gain, which means there's no, even you see there's a transfer function, there's some S there, but they don't change anything. They don't change the phase. From a delta VS all the way to the TE will basically just amplify the signal or make it be smaller. It doesn't change any phase information. If this is pure gain, then whatever K you put there will become the additional damping coefficient. But unfortunately, the transfer function from delta VS, so from the input of exciter until the electric power is not a pure gain. It does have some phase. So that one usually has phase lag characteristic. Phase lag characteristic, which means if your input signal is like a variation at a certain phase, and you measure the output, the phasing will be lagging the input by a certain angle. Okay, usually that angle should be maybe from 0 to 90 degrees, because if you still want the input output pointing to about the same direction, but they will only separate by angle less than 90 degrees. Then you also compensate. So this, which means this angle may subtract certain angle, right? Going through this process. So which means this PSS need to add certain angle to compensate that phase lag. So the design of this transfer function need to enable to add a certain angle, and that angle will compensate that negative theta. Then eventually this gain will give you additional damping coefficient. So that's the idea of a power system stabilizer. Okay, let's just consider a very simple example. So here I draw the bow diagram for the 3 blocks, starting from exciter, field circuit, and all the way to the electric torque. Okay, so I only just consider this one as maybe first order system just for simplicity. It will have some time constant t. T just means total time constant. So everything there, if you count the delay of each component totally, they will give you the total capital T. That's total delay. And we just use this first order system to approximate. If we draw the bow diagram, the first one is for the amplitude. They just tell you the amplitude will be decaying, and when you increase the frequency, when frequency is high, become higher. At a steady state, it doesn't change anything. At steady state, the amplitude is 0, which means because this is like a logarithmic, so 0 means it doesn't change any signal. But when you go to the high frequency, the value will decrease. So this is like a low pass filter. For the phase, it will introduce around that time constant about -45 degrees. If this one can be approximated by first order system. If it's second order system or third order system, that angle can be higher. But here we just treat it, maybe the phase lagging by the exciter is not too much. It will be like between 0 to -90 degrees. So for this case, it will be -45 degrees. Okay. Then we need to make a PSS to compensate that -45 degrees around this time constant. So it will give you this additional. So this one will be the phase plot of the PSS, and this will be the amplitude of the PSS. So the blue one will be the transfer function from the input of exciter to the electric power. The right one will be the transfer function of PSS. So when your signal, your frequency division first goes through PSS, then go through the exciter until the electric power, the final transfer function will be will be this one, will be this pink one, will be somehow in between. Or you just add the blue phase, negative blue phase to the right positive phase. It gives you around 0. So here, around the center time, the phase shift is about 0. And at that time constant, you get about this gain. So this one will be your actual additional damping coefficient to be increased by PSS. So in order to give you this phase lead characteristic, the PSS has to have 1 pole and 1 0 for the minimum. You can have multiple poles, multiple 0, but it need to have at least one 0, which is characterized by T1, and maybe one pole. Just make it this stabilizer is easy to be realized. Otherwise, you can write arbitrary transfer function, but not everything can become practical. But this is like a minimal implementation of the power system stabilizer. And in order to have this transfer function to provide a phase lead, which means the right one will have positive phase. T1 has to be bigger than T2, okay? Because I draw the two lines. The first one is actually determined by the 0, which is T1. Because the time constant T1, the 0 will be 1 over T1. 1 over T1 has to be smaller than 1 over T2, which make T1 be bigger than T2. Only that condition is satisfied, you will provide some phase lead. But how much to provide, you still need to design T1, T2. Okay, so if a T1, T2 is too separate from each other, maybe phase lead is smaller, or maybe it's T1 is close to T, but T2 is too high. It may also not give you a desired phase lead. All right, so let's see. Finally, this will be the final transfer function from speed division until electric torque going through PSS and excitation system. So the transfer function will be that of the PSS and also the transfer function with the excitation system, because we already derived the detailed transfer function for excitation system from previous slides. Now you just need to design this one, the minimal implementation basically just 1, 0, and 1 pole by using the tau 1, tau 2. Okay, so you plug in the transfer function of the blue one and the red one. So you do some simplification. Finally, you will have something like this one. Okay. If I just give you the very simple simplified version. So here the tau sigma, T sigma just means the total time constant, everything in the denominator. And this one, if you make a denominator be a real and you make a imaginary number to the numerator, and then finally you will have this one. It will have real part, imaginary part. Real part will be the damping torque, and imaginary part using the formula we proved, right? This one, whenever you see J multiplied by delta, this one also always can be translated to something related to delta omega, which is here. So if you forget that formula, what we proved. So whenever you see J multiplied delta, delta can always be translated by this one. So you'll create a damping component. All right, so finally, what we expect to have by designing the PSS, we expect to have this component to be positive. And this component is not negative. It can be small or 0, but it should not be negative. That will make the PSS be able to provide positive damping and also doesn't not affect the angular stability of the machine. It will give you the positive damping torque and also improve a little bit of the synchronizing torque. So this is usually what we expect by PSS. So it has to be a phase lead compensation component. And if we want both component, damping component and the synchronizing component be positive, somehow we call it under compensation. Under compensation, which means we doesn't have to completely compensate that negative 45-degree angle. We can make it be a little bit smaller, like less than 45 degrees, such as this one. As long as this one positive and this one, it can leave some value there as long as it's not negative. Okay, so this is our idea of designing the PSS. This is the real PSS model. So the input is the speed deviation. The output will be going to this sigma is just around the exciter. It just added to other voltage control signal to the exciter. Compared to the theoretical model from previous slide, so we know this is gain. This is how much damping coefficient you want to add. This is like just basically just additional KD you want to add to the system. This is the phase lead compensation. Okay, and this one is called washout component. Washout component is just it's high pass filter. It try to filter out some very low frequency. Because very low frequency can exist in the speed deviation because the system may have low variation all the time. So you will see the frequency deviation. There's some oscillation is very slow, but it doesn't really mean generator is oscillating. It just means the load condition is changing. So you want to use high pass filter to filter out those signal and keep the real oscillating signal. Okay, so typically this washout block will have a time constant. We can take maybe 1 to 20 seconds. And so 1 second, which means it will keep all the oscillation about 1 Hertz, right? 20 seconds, which means it will it will keep oscillation above 0.05, right? 0.05 hertz. Yeah, anything like above some oscillation above 0.05 hertz can go through this channel. And the phase compensation block, usually you want to define the T1 and the T2, and T1 has to be bigger than T2 to make it behave as phase lead compensation. So if a T1 is smaller than T2, that becomes phase lag. That will give even worse oscillation. You want to have T1, T2 to cover a range of frequency. That will be your dominant oscillation frequency. So usually you want to cover a range from, for example, 0.1 hertz to 2.0 hertz. So this is typically means electromechanical oscillation. Higher than 2.0 hertz, usually it may still be some electromechanical oscillation, but will be very, very local. It doesn't cause the stability concern of the system. So from 0.1 to 2 hertz will be the most critical range of frequency. You want to improve the angle stability. For instance, if we put TW as 10 seconds, which means we'll start filtering out some frequency lower than 0.1 hertz. And T1 and T2, we take a 0.4 and 0.04 second. That will cover the range from 0.4 to 4 hertz. Okay, and if you draw the bow diagram, this will be the PSS. Please note, usually if you use MATLAB to draw the bow diagram, and the x is actually not its frequency, but frequency in radian per second, which means this is actually omega. So you still need to divide this one by 2 pi to get the real the frequency in hertz. Okay, so this range will be from 0.4 hertz to 4 hertz. And this frequency, any signal lower than this frequency will be somehow filtered out, even it's not perfect. And you see the part, so this is like 45 angle. So this point, the center point, will be the maximal phase compensation. So it will give you above 45-degree compensation. So if your excitation system has negative 45 degree, and this one will give you positive, about 45 degree. This picture is basically the same model. If you use a PSSE software from the manual, it gives you this model. So basically same, but it will allow you to utilize 3 components to give you more phase lead compensation. So each component gave you about 45 degrees. So if you really want to expand this range of frequency to cover wider range of frequency, you can use the multiple component to give you better phase lead. This is the slide of the PSS. Okay, so we by this slide we finish everything about the excitation system. Okay, we can move to the real stuff of small signal stability. Small signal stability is also referred to as small disturbance stability. It basically just the ability of a power system to maintain the synchronism when subjected to a small disturbances. In this context, the disturbance is considered small if the equations describing the system response can be linearized for analysis. So we have talked about this one in the background session. So here, let's see, we have a nonlinear system. So I star equals a negative fx. Okay, the negative fx will be the vector field that determines how the state variable will change. If I certain I0, the vector field will take value 0, which means that will be an equilibrium point. And if that equilibrium point is stable, that point we call stable equilibrium point. Okay, so for this case, this point will have fs equals 0, so it will be a stable equilibrium point. So if you only interested in a very little neighborhood of the equilibrium point, for instance, this very little blue rectangular area, and you study how the system responds to any small disturbance in this area, and you can linearize this vector field by the first order derivative at the equilibrium. Okay, so if you compare the black curve, which is accurate vector field, versus the blue line, they're very close. Okay, if the difference can be ignored, which means you can use the small signal analysis, stability analysis method to study the response and stability. So you can move the coordinate to that equilibrium and only study the deviation of the state variable, okay, using this linearized formula. So the system is stable only if it can return to the original state, which is a stable equilibrium point. So for the behavior in this very small neighborhood, we can use the linear system, linearized model, and there's a lot of conclusion from a linear control theory we can utilize to study dynamic of the system. So if you use my handout from the early version, on that case, I didn't add this negative sign. The purpose to add this negative sign, because in this figure, I draw the slope with positive. In order to make this system be stable near that x0 point, the original equation has to have negative sign. Otherwise, the system is unstable at that point. But that x0 can still be equilibrium point. The equilibrium point only need to make this equation be 0. Okay. Small signal stability method or analysis can be applied to both stable equilibrium or unstable equilibrium. It doesn't matter. It just whenever you study the behavior of the manifold near equilibrium and using linearized model, the small signal stability method can be used. Okay, but if we want to focus on a stable equilibrium point, and that equilibrium has to be stable. For convenience, it is assumed that the disturbance causing the changes have already disappeared, and the detail of disturbance is important. So in the rest of this session, we don't worry about what the disturbance is. Even under some example, we say, okay, we assume there's some change of the angle speed, but usually we don't dig into what really happened, which line is tripped, what short circuit occurs on the system, right? We don't worry about the details because we only want to focus on the response in a very small neighborhood of the equilibrium. So in the rest of section, we'll first work on a very simple power system, which is single machine InfiniBus system. We start from this system, we'll linearize the system equations. Then we use the linearized model to study the system response. Because here we pay more attention to some oscillatory dynamic of the system. We'll generate a number of methods to study the oscillation of such system. Then we'll move to a general power system with many generators, and we'll also go through the same process to first linearize the system model. Then we study the different type of oscillation modes. The first how about this single machine InfiniBus system? In this system, we have a single generator, which can be synchronous machine or synchronous generator, depending on the direction of power flow. And it connected through a transformer, and maybe here is the 2 transmission lines and 2 InfiniBus. InfiniBus is basically some voltage source, like constant voltage source, which has this voltage which is constant and never change no matter what happened in the system. So usually infinity bus means a very large system. It's not a low, right? So single machine infinity bus system is not like a single generator, single load system or single generator system. It's not correct to call this system as single generator system or single machine system. That's wrong. It's called single machine infinity bus system because that infinity bus is another infinite system. Infinity bus here is like a Earth, right? When you study a very simple motion in the mechanics, you want to study object moving on the ground. The ground is not outer space. The ground is actually the Earth, right? You study that object moving along relative to Earth. So you actually study a two-body system, not a single-body system. For any physical system which to be meaningful, usually you need to study at least two bodies. So here, for any power system to be practical, you need to have at least two generators. So one generator will be this single machine. The other generator will be that infinity bus. Okay, it can be just infinite generator or maybe a large system which can be treated as infinite generator. If you create a circuit model, on both sides you can put a voltage source. And if we use the infinity bus as a reference, so that we just call that angle to be 0, then the generator will have angle delta. So E prime here is just the transient voltage, which is same as the E prime we define in the generator modeling session. And total reactance, including the transient reactance in DSs, and also the total reactance along the entire transmission path, together will be the total reactance connecting this EMF or generator to the infinity bus voltage. All right, so here, because we're going to start writing some equations involving some state variable and parameters, and we have to define a unit. So H is an inertial time constant, which just have unit second. Delta is radian. KD is a damping coefficient in per unit. The mean is for 1% of frequency change, it will cause 1% of power or torque change. And torque and power will take per unit, so which means for either just mechanical power or electric power, the mechanical torque and electric torque will take the same value in per unit. The special one will be, we want to keep the rotor speed in per unit because we don't want to see the omega 0. Omega 0 is the actual synchronizing frequency. Synchronous frequency, I want to just make equation be simpler, and here we specifically require omega r in per unit. Okay, then we can start writing the swing equation. So this swing equation is same as the swing equation we derived from the generator modeling session. The only difference is here. So in that version, we don't have this parenthesis. And we have here, we divided by omega 0. And here we divided by omega 0. And this one is omega 0. But because we let omega r take a unit per unit, so we somehow change the writing of the equation, but it's about the same side of the equation. Okay. So which means omega r is in per unit, and subtract 1, which will give you speed deviation in per unit, and multiply by omega 0 will give you the speed deviation in radian per second. And the good thing is we don't see that omega 0 under the 2h. So that will make the second equation simpler, but it's about the same equation. The electric torque or electric power in per unit can be calculated based on this formula. It will change as a sine function of angle. And this one, we can call it the maximal power. that means the maximum active power you can deliver from the generator to infinity bus. This is very useful limit. We're going to consider this one also in next session. So if we draw the power angle curve, so this will be the operating point, currently the operating point, to make it the mechanical power be same as electrical power. So that will be this is called a stable equilibrium point. Definitely this point is called unstable equilibrium point. They're both equilibriums. And here is at the limit. All right, so next we want to linearize the model. We change the coordinates to the stable equilibrium point. So we build a local coordinate at that equilibrium point, and the new state variable will be the deviation of the angle and the speed. So this will be the new swing equation. And the difference between the mechanical torque and electric torque is the same as the difference between their variation. Okay, so we'll take this version. The next thing we want to linearize the power angle curve near the stable equilibrium point by this straight line. So we use this straight line to approximate as a sine function. So that can be very accurate if it's a very small neighborhood near that equilibrium point. So we do the linearization. That will make the electric torque deviation to be roughly proportional to the angle deviation. Okay, then we'll have this formula tell you what the synchronizing torque coefficient is. Okay, basically just first order derivative of electric torque with respect to angle at equilibrium. So now we have this linearized version of the single machine infinity bus system. So we'll start from here to study the response of the system. Let's first create the state space representation of this linearized model. We can first draw the block diagram. So this block diagram is very similar to the block diagram we have seen in the generator modeling session. But here we add another component, which is a synchronizing torque component. Okay, this one comes from the system. The rest of the everything, okay, so everything else is actually may only come from the generator itself. But the KS really come from that sine function. So that sine function is the electric power from generator to the infinity bus system, infinity bus. So that, which means this KS is really from the network. The state space representation can have this matrix form on both sides of the equation. So basically they are exactly the same set of equation. We just introduce the vector, state vector, including both delta delta and delta omega r. Another thing we can do is we can eliminate the first the state variable delta omega r. We just plug in the first equation to the second. Then we only have delta delta. So we'll have a linear second order differential equation. If we apply Laplace transform to this equation, so first one will become S2 S squared delta delta, and this one will become S delta delta. And then you do some simplification, you'll have the solution of delta delta in the frequency domain. Okay, so then if you apply the inverse Laplace transform, you'll be able to get the response in time domain. This component, is called the characteristic equation, which is similar to the characteristic equation for the frequency regulation and voltage regulation system, right? Whenever you derive the transfer function, and which is closed loop transfer function, and the denominator will give you the characteristic equation, because that will tell you the poles of the system. The poles will determine stability. So stability of this system, or in other words, if there's any disturbance or input, if this rotor angle can be stable, this characteristic equation have to have all the poles which are on the left-hand side of the compliance plane. We'll go to that later. All right, so before we study the response of single machine feedback system, let's first consider a linear oscillator, which is harmonic oscillator. So this harmonic oscillator has a subject or mass with mass of m on a surface. So the surface may have friction and connected to a spring starting from a fixed point. And if there's no if this subject is not moving, it will stay around some point. We just call that equilibrium point. But if it's in the dynamics, so it will oscillate near that point. So we can define the positive direction for x separating from that direction as x. Then based on the second Newton's law, we'll have the first equation, right? The force of of m is equal to the mass multiplied by the acceleration. And the second equation is based on the Hooke's law. It determines if there's spring and the coefficient is k, so force will be equal to negative ks. And if the system also has some friction, the friction can be proportional to the speed. So you would need to add this item. So for this system, you can definitely have this second order linear differential equation. So the characteristic equation of this system will be this one. So if you compare the characteristic equation to that of the linearized single machine infinity bar system, they look very similar. All right, so the m is the mass of that object for the single machine infinity bar system will be 2h. 2h is actually the time constant. You need to speed up the generator from 0 speed to the nominal speed at the rated power. The d on that harmonic oscillator is some friction. So here kd is like damping coefficient, and k on the single machine infinity bar system is correspond to ks, synchronizing coefficient multiplied by the singular speed. Okay, for such harmonic oscillator, for the characteristic equation, there's a standard form. The standard form will have the constant part. Usually that one is positive. We call it omega n squared. And the coefficient, the first order term coefficient, we call it 2 zeta omega n. Okay. The zeta here is called damping ratio. Omega n is called natural frequency. This is the standard form, which means if you have any characteristic equation, second order linear characteristic equation, and you compare that equation to this standard form, the next step you can solve omega n and zeta will give you the damping ratio. Omega n will tell you the natural frequency. So they both have a very meaningful indices to study the response of this system. Another way to obtain those zeta omega n is you can solve the two solutions, so two roots of this second order characteristic equation. So if this equation describes an oscillating system, So S1 and S2 here are both complex. They are not real. So if S1 and S2 are both real, this system cannot oscillate. So S1 and S2 have to be a conjugated pairs of a complex roots, which correspond to the eigenvalue of the system. If there's no input on the system, okay, you only just release that object from another place different from the equilibrium. That is called zero input response. So it will become autonomous system oscillating around the equilibrium, and the trajectory of oscillation for the state variable will be sinusoidal waveform with decaying amplitude. All right, so assume the two roots of the characteristic equation are S1 and S2, and they are conjugate pair with the same real part and opposite imaginary part. So real part is called sigma, imaginary part is omega. And if you solve this standard characteristic equation, you can easily prove the real part will be negative zeta omega n. Imaginary part will be omega n multiplied by a square root of 1 minus zeta square. Then if you solve the response in time domain for this system, the response has to satisfy this formula. It will be a damped sinusoid waveform. The A determine the initial amplitude depend on the initial state. So that one can change with the disturbance. And the sinusoidal part will have frequency omega. So that omega will be the imaginary part of the roots. And also there's an exponential function, the sigma. Sigma will come from the real part. And there's another atom, which is the phase. Phase also depend on the initial time. Okay, so that will be the initial phase at the time 0. You can also write the response in this form using the standard characteristic equation. Okay, so now instead of using sigma and omega, you're going to use zeta and omega n. So if you want to draw the waveform, okay. By the way, so if we know this the expression in the time domain, we can estimate the time to decay to around 37%. Okay. Remembering where we introduced this index. So whenever you have something like this one, so there's a tau, which is time constant. If you can write any time function in such a way, exponential function of time, and the tau tell the time decay to about 37%, which means after the time of tau, the majority of the amplitude has been decayed. And for this case, because we know the exponential function will have exponent sigma t, so we immediately know the tau will be negative 1 over sigma, or tau will be 1 over zeta multiplied by omega. Okay, so if we give some value, so this omega actually means the observed oscillation frequency. Let's try give it some typical value. For this case, sigma is negative 0.5. Omega is 1. And phi is 0. A is 1. You will see this waveform. Sorry, yeah. Omega, sorry, here is not omega 1. Omega is 2 pi because another way. Actually, the frequency is 1. Omega will be 2 pi because this is omega. Okay, so why is frequency 1? Because if you check the time between two peak value, that's 1 second. Right, that's 1 second. Because here is 1, and at 2 seconds, it will have it start from the peak value at time 0, and at time 1 second, it has second peak, and the third peak happens at the time of 2 seconds. So every 1 second, it will go to the peak again. So omega here will be the angular frequency, which means frequency will be omega divided by 2 pi. For this case, f is 1, so omega will be 2 pi. Okay.
2 pi is the natural frequency or the operating?
2 pi, whatever here in that sine or cosine function here, it is what you observe frequency. Or maybe, yeah, I just noticed this is cosine angle, so which means the phi is not 0. What is phi? Maybe 90. Phi is 90 degree or 90. Let me see. -90 degree, right? Yeah, phi is not 0. Because I assume it starts from peak value. But anyway, so because phase is not important. So omega here is observed frequency. Omega n means if the damping becomes 0, that will be the frequency. So typically they are very close, but they can have very slight difference. For instance, what I mean is, if you have a equal amplitude oscillation, okay, and this will tell you the true period, right? I call it, maybe I use capital T, it means true period. 1 over capital T will tell you the frequency. And you translate that frequency to angular frequency, that will give you omega. From here, it will give you omega. And because it doesn't have damping, it will have equal amplitude. This omega is also omega n, same. Because omega is equal to omega n multiplied by the square root of 1 minus the zeta squared. All right, so but now if there's a damping, which means the oscillation will become smaller and smaller. So what this waveform change will be something like this one if I use different color. So it will add some envelope. The envelope tell you basically tell this part how the amplitude will decay. So when you multiply the original right waveform by this amplitude, what happens is will make the value after this peak value will be lower. Because this amplitude is not symmetric about each point on the peak value, it will make the actual peak value, if we really mean the maximal value in each period, that will be slightly shifted from the original peak value. So that will make, finally will make omega be slightly smaller than omega n, only slightly, if the sigma is very small. So typically, we don't worry about which really mean the frequency. You can use either one. Okay. But basically, omega without n means what you observe the frequency. If you use a data-driven method. You try to identify the maximal point and try to measure the distance, and the reciprocal give you the frequency. That will give you omega. But if you start from the formula, you know the damping ratio, omega n is called the natural frequency. All right, so let's look into the natural frequency and damping ratio. If we draw the two conjugated eigenvalues or the two roots of the characteristic equation as a pair in the compliance plane, they will be symmetric about the real axis. It has the same real part and opposite imaginary part. And if we draw a phasor connecting the origin to either root, it will give you an angle, which is this theta angle. So that theta angle is equal to arc cosine theta, or arc tangent this expression. Okay, so theta basically just characterize the angle from the real axis to either root. If we compare this standard characteristic equation to the equation for single machine infinite system, and for that system, we know the synchronizing coefficient can be calculated by this one, and we define omega as the observed oscillation frequency, and we call negative sigma, because if the system has positive damping, the sigma need to be negative. So negative sigma really measure how much damping you have. We usually expect this one to be positive, but not zero. So this one will be equal to the product of the zeta and omega n. And if we utilize the formula for KD and KS from the single machine infinite system, and we can get this very useful formula to tell you the oscillation frequency. And we can also get another set of a useful formula based on the characteristic equation of the single machine infinite system. We can calculate natural frequency and zeta. The zeta is damping ratio. So why zeta is called damping ratio? Because usually we call the negative sigma as damping in general. Zeta is defined as the damping, the ratio of the damping to the natural frequency. Okay, so if you know the natural frequency, you multiply by some ratio that give you damping. So that's why zeta is called the damping ratio. So those formulas are very useful for you to calculate the either omega, sigma, or omega n and zeta. Please note here the unit for KD, which is in per unit, and Ki is in per unit per reading. Okay, let's see how the frequency of oscillation may change. If we, for example, if we replace a lot of conventional generators by renewables, the total inertia will reduce. And the transmission may become weak, and if we also increase the load, so they all seem to be something not good to the system dynamic. So you have reduced edge, increased readiness, and increased the delta zero. How does the frequency change? So if we reduce edge, will the frequency increase or decrease? We will utilize this one, right? So if edge increase, so this one will decrease. How about what if the readiness increasing, it will cause similarly, right? They will frequency decrease.
Edge is decrease.
Oh, sorry, yeah, H decrease, omega n will increase. Yes. So if loading increases, which means delta zero increase. So delta zero increase, cosine delta zero will become smaller. So frequency will decrease. All right, so if your system has reduced inertia, the oscillation frequency will become faster. Oscillation will be faster. If the connection or transmission become weaker, then the frequency will become lower. You'll have slower oscillation. And the loading increase, also the frequency become lower. So later we can utilize those conclusions to study the dynamic for a larger system. Okay, next we want to solve the response of the single machine feedback system after a small disturbance. Because it is a small signal stability analysis, so we don't care about the details of the disturbance. We only worry about the damping or the amplitude of the oscillation from the response. We make a delta be first state variable and delta omega be second state variable. And we also make this one be the input of the system, because we're familiar with, so remember the standard form of the state space representation will be, so we'll have plus B and U. This is what we know about the linear system in the state space representation. So we just assume the mechanical power change will be modeled as input of the system. All right, so we replace delta and omega by S1 and 2. We'll have this equation. We match this one to the standard state space representation. We can assume some output. For this case, if we assume the angle and speed can be directly measured, this output channel will be modeled by a unity matrix. Okay, so Y here basically same as the state variable. But if you are not able to measure the angle speed directly, so this C matrix will not be identity matrix. First, we apply Laplace transform to this equation. And we assume the input as the step function. So step function will be proportional to a 1 over S. Okay, then we solve the output. And so there will be first two items. The first one depend on the initial state. The second item depend on the input. So if we only have the first item without the second input, if the input is 0, then we solve the system response. That's called zero input response, or state only response. So if the initial state is exactly at a stable equilibrium point, but we give it some input step function, so that will be a zero state or input only response. But if you have initial state not at equilibrium and also have non-zero input, you will have both, right? The response will be more complex. So next we can solve the state variable and in frequency domain. We translate it back to the original state variable, so we have the formula for angle and speed response in the frequency domain. So the response is a linear combination of two response. First is zero input, the second is zero state. Okay, they both will go through this transfer function. So next, if you do the inverse Laplace transform, you'll get the expression in the time domain. So we start from here. and we'll derive some useful formula to calculate zero input and zero state response. For zero input response, we have to give some initial state, not at equilibrium point. Because we have two-state variable, you can add any perturbation to either one. For instance, we assume the rotor is perturbed such as it will have some initial angle. So you don't have to ask how this angle is generated, but it just starts from a non-zero angle. We define that time to be a time zero. And fortunately, that speed deviation is zero, which means at that time point, the angle deviation is non-zero, but speed is still 60 Hertz. Okay, so this is very simple scenario, and then we'll have those two formulas on the angle deviation and speed deviation in frequency domain. For the zero state response, so here we assume the initial state is at exactly the equilibrium, but we make the input be non-zero. So it gave it some deviation of the mechanical torque. For instance, this one can be caused by the governor. By changing the setting point, you let the generator to generate more power if this is positive. It will have these two formula. Then we do inverse Laplace transform. We get the time functions for angle and the speed deviation. So here the theta is just the R cosine, the damping ratio angle. It basically just angle of the complex rules. Okay. You can use this approach to find other time functions of the more complex system response. So on the Sadek's book, example 11.2 and 11.3, so it gave you some value so you can solve the response for zero state and zero input response. For zero input, it will assume some initial angle. For zero state, it will assume some change of the mechanical power. This is the zero input response. So you see the angle start from this is the equilibrium point, and they add some additional angle. So it will start from here. And the angle will oscillate. So eventually we'll go back to the equilibrium point, which is 16.79 degree. Okay, frequency start from 60 Hertz. It will oscillate and go back to 60 Hertz. That's zero input response. For zero state response, it assumed the mechanical power increased by 0.2 per unit, like 20% of the base value. So angle and the frequencies both start from a regional equilibrium point. But because you increase the input, you will create a new equilibrium point. So finally, the angle will stabilize at the new angle. This is new equilibrium point. So this is new SEP. So those two I treat old as old SEP. So those two are new SEP. Okay. All right. Any question on the single machine feedback system? All right, next we'll move to more general cases for power system with many generators. We definitely can borrow similar analogy with a harmonic oscillator, but for a more general power system with many machines, and sometimes it's hard to say which machine can be considered as harmonic oscillator. Oscillating, it will involve a lot of generator, but we still can somehow borrow some analogy from this mechanical system. So we can treat each generator as some pendular. It will be some weight connected by like rubber band, and with some neighboring weights, a neighboring generator, and eventually will be connected to the ceiling. The ceiling will just mean somehow like infinite system. Okay, so in this power system, if we can treat each generator will be somehow like a pendular, and they all connected through the rubber bands, which are transmission lines. If there's any disturbance, definitely each generator may oscillate, but we also observe many generators tend to oscillate together. They behave about at the same phasing of frequency. Like if there's oscillation, there's some generator, they stay very closely, which is like a group. There could be another set of generator, they behave as a different group. So the entire system is synchronous. No generator become out of step, but it somehow form some coherent group. So maybe we can reduce the system based on the coherent group, and then we can study the oscillation between those groups. So a power system naturally enters periods of oscillation as it continually adjusts to a changing operating conditions or experiences disturbances. So even there's no fault, because the change of load or change of the power, it will change the input of generator. So it will still cause some response of the system, which will cause generator to oscillate. So if you are an operator and if you are able to get real-time data, you will see the most of generator they oscillate all the time, but most of time and the oscillation is very small. It doesn't cause any concern. And because the network has some resistance, when the generator oscillates, the power flow also oscillates, and the current squared multiplied by R will tell how much loss along the transmission. So the transmission loss definitely is not good for any efficiency, but they can help reduce amplitude of oscillation. When there are many generators, you will be able to see many different oscillations at different frequencies. Usually we consider oscillations higher than 1 Hertz as fast oscillation and lower than 1 Hertz as slower oscillation. The higher frequency, the higher the frequency, the faster the damping. Why? Because if we go back to that simple case, even for the same damping ratio, if you increase the frequency, even you keep the same damping ratio, it will damp faster, right? Because its amplitude will decay much faster. So if you keep the same damping ratio, so which means faster oscillation take shorter time to be damped. The slower oscillation will take a longer time to be damped. The power system operator does not want any oscillation, okay? But if he has to choose, usually the fast oscillation is better than the slower oscillation, because slow oscillation will take a longer time to be damped. So their study will focus on, or monitoring will focus on slower oscillation, not fast oscillation. A power system can naturally damp high frequency oscillations, whereas low frequency oscillations are more damaging because they can persist for extended period, become sustained, or even trigger some protective relays. Okay. So which means if the two objects oscillate too much, eventually some protection may break the transmission. So that will cause more disturbance on the system. All right, so I stop here. Okay, we'll continue on next Tuesday.